In this section, we will learn about optimization. Our goal here is to create a model and find the maximum or minimum value for that model. Most of these problems are going to be word problems. So first thing we want to do is kind of take a look and see the steps that would be necessary to address these sort of word problems. So the very first thing you always want to do in any word problem, especially here, is to make sure you understand the problem. Read it carefully, look at the question of what you're asked to find, and make sure it's completely clear. Ask yourself, what are the unknowns? What are the given quantities? What are any given conditions in the problem? Next, draw a diagram if necessary. Right? So not all problems are going to need a diagram, but if they do, it may be helpful. Assign variables to the quantity that is to be maximized or minimized, and any other quantities in the problem. Right? So that makes you look at the problem, understand what the functions are going to be and what are the variables that are involved. Next thing we're going to do is write an equation for that quantity, the one that we're trying to maximize or minimize, and write as a function of the other variables in the problem. If your function has more than one variable, what we're going to do is try to establish a relationship between the different variables in there and try to get rid of those extra variables. Currently, we can only optimize equations or functions that have the function that's in terms of one variable, right? So we're going to get rid of the extra variables in the problem. And it's a function, so we have to write the domain of the function. And on a closed interval, we want to make sure as we optimize, we consider the endpoints of the interval as possible places where the function could have been maximized or minimized. And then go back to the methods that we had learned in the past for finding absolute max or mins. And again, don't forget to pay close attention to what your domain is in the problem. Right, so we'll look at an example next. Okay, let's take a look at an example. So in this problem, we have a nature preserve that's trying to protect an endangered species by fencing off part of their habitat. And we're told that the area is adjacent to a river and the site that's next to a river doesn't need any fencing. They have limited funds. They have a $70,000 grant to pay for fencing, and the fencing costs $10 per foot. And we want to know what's the biggest area that they can actually fence off, right? So first thing we always want to do with any kind of word problem is make sure we understand what the problem is talking about. And I don't mean the mathematics of it, but the actual practical sense. So I'm hoping this one's not terribly complicated. A picture sometimes does help. So there is a river. So let me just kind of try to draw a picture. So there's my river, my best attempt at it. And next to it, there is a rectangular area that they want to fence off. And again, the riverside does not need fencing, so they are going to need fencing adjacent to that river, and it's going to be a rectangular area, right? So, and they need to pay for those three pieces of fence that I just drew, right? So that's kind of what's the problem's describing. Next thing I'm going to do is go back and make sure I understand what it is I'm asked to find, right? So not the information that's given. It's not always clear how information in a word problem needs to be used. We always start with the question and then see what pieces of information is necessary for you to answer and what pieces we can ignore, right? So in this case, we're asked to find the dimensions for the largest area. So I'm asked to optimize the area of this rectangle. So let me start by writing the formula for area of a rectangle. So I'm asked to find the area of a rectangle. I know the area of a rectangle is length multiplied by the width. And I'm gonna just label my shape with length and width. Doesn't matter which one you call which, right? And I know since it's a rectangle, if I call this side W, this side is also gonna be the same length, right? So the next question I ask myself in this case is, well, what stops me from making this area as large as it can be, right? To ask me to find the largest area. Well, my limitation in this case is based on the cost of this, the fencing that I need to buy for this area, right? So we only have $70,000 in our pocket, and we have to pay $10 per foot. So those are what limits this area to be as big as I want it to be. I got to stick within my budget. And the other question that should pop into your head is when you look at this formula for the area, we need to optimize it. Now we've learned how to find a maximum and minimum for functions, except all of those methods that we have learned rely on us only having one variable, right? So we have find the maximum minimum for function f of x. And in this case, I have a function for the area depending on two variables, both length and width. And currently, we don't have the tools to address that sort of a question. So there are a couple things I need to do is somehow try to eliminate one of these variables, and we do that by finding one in terms of the other when possible. And also make sure that we account for how much money we have. Right? So and both of those kind of go hand in hand. So I'll start with our constraint in this case, which is the $70,000. And in my picture, I can see that I need to buy two lengths that we call W and one length that we called L. And each of those costs $10 per foot. So if I do this, so $10 for each foot of W plus $10 for each foot of L plus $10 for each foot of the other W, that has to be, can't be more than $70,000, right? And if I'm trying to find the largest area, I want to make sure I spend as much money as I can. So we're going to set this equal to $70,000, right? So that's our constraint. The next thing we're going to do is solve this for one of our variables. Well, actually, let me simplify it first. I can combine my W's together. I get 20W plus 10L equals $70,000. And then solve this either for W or L. I'm going to solve it for L. If you try to solve it for W, you have to divide by 20. And 20 doesn't divide into 10 evenly. You're going to have a fraction. But if I solve for L, I have to divide everything by 10. And 10 does divide into all my numbers. So it's going to give me nicer numbers to work with. So I'm going to solve this for L. So if I get 10L is equal to 70, excuse my handwriting, 70,000 minus 20W. Divide everything by 10. I get L equals 7,000 minus 2W. So next thing we'll do is take this and replace our L in our equation with that quantity. So area is going to be now 7,000 minus 2W times W. And now I have an equation that only has one variable in it. If I distribute the W in there, I get area is 7,000 W minus 2w squared. And I can go ahead and optimize this, find the maximum. Before I continue, I want to make sure that I have my domain and make sure the answers that I get are acceptable. And if I'm finding the absolute max or min, I want to make sure I do consider the endpoints of the interval if it's a closed interval. Right? So in this case, there are no algebraic restrictions to this. It's a polynomial. So I don't have anything to worry about algebraically, but practically, there are some things I have to worry about. So my w in this case isn't just any variable. It represents the width of a rectangle. So it needs to be a positive number. So as far as my domain is concerned, I need to make sure my width is bigger than 0. And it can't be 0 either, otherwise I won't have a rectangle. I'll have a minimum area of 0. And I also want to make sure how big it can be. And in this case, that also has a restriction. My width can't be infinitely large, again, because I had a limited amount of money to spend. So there is only so much width I can have to stick within the $70,000 budget. So I'm going to go back down here and look at the expression that I had. The length is 7,000 minus 2w. And you should notice from there that if my w gets too big, my length is going to turn out to be negative. So in this case, the biggest w I can have is 3,500 feet. Otherwise, 7,000 minus 2 times w would become negative. And again, this equation is the result of our constraint, our budget constraint. So that I'm looking at the simplified version of that equation. So my width in this case cannot go beyond 3,500. And again, as soon as it hits 3,500, once again, my length would become 0, and I wouldn't have had any area left. All right, so now I have an equation. I have my domain, and all I really need to do is go back to the methods we had learned earlier to find the maximum or minimum of a function by taking its derivative, setting it equal to 0, and solving. So let me do that. I'm going to take the derivative of this function. A prime is going to be 70,000 minus 4w. Set that equal to 0. Right? Because we want the derivative gives us the slope, and at maximum or minimum, the slope is going to be horizontal. Solve this for w. 7,000 equals 4w, divide by 4, and so we're going to divide 7,000 by 4, and 7,000 divided by 4 is 1,750. And it does fit within our domain, so it's an acceptable solution. And the next thing I need to do is go ahead and also find the length, because I was asked to find the dimensions. So so the length is going to be 7,000 minus 2 times w, right? So I'm using this equation that we had earlier, 2 times 1,750, and 7,000 minus 2 times 1,750 is equal to 3,500. So the dimensions that would give us the largest area would be a width of 1,750 and the length of 3,500. And again, our domain was not a closed interval, so I don't really have to worry about 0 and 3,500. But even if it was a closed interval, if I go back and use those, in one case I have a width that's 0, which gives me a 0 area, and in the other case I have a width of 3,500, which results in a length of 0. And once again, I will have 0 area. Um, and you can always plug these numbers in to find the actual area, but the problem just had asked me to find the dimensions.